from the University of Toronto, specializes in the dynamics of droplets and space. His research covers heat transfer, fluid mechanics, and material sciences, applications in spray coating, cooling, and waste heat recovery. A co-founder of Center for Advanced Coating Technologies, he has developed advanced spray cooling techniques and thermal management innovations.
So much
Professor Chandra has received the Brockhouse Canada Prize in the year of 2010, the Jules Stachewitz Medal in the year of 2015, and is a fellow of Canadian Academy of Engineering and ASME. Today, he will present on two-phase flow and liquid cooled heat sinks made by additive manufacturing. Welcome.
Thank you. Thank you for the invitation. Thank you all for holding on. I know it's the last presentation of the day, but just a little more time. So, this is a workshop on two-phase flows. And I'm going to be talking about two very different types of two-phase flows. So, first, I work with sprays, and these are metal sprays, and we want to use them as additive manufacturing. So, I'll talk about that. But then we use these to make heat sinks, and we look at two-phase flow within the heat sinks. And I'll be talking about that this way. So, a number of people have talked about the importance of electronic cooling. That is also our big focus. And we know the importance from first-hand experience because we collaborate very closely with people in our electrical engineering department. They give us the circuit boards, we are supposed to cool them, and if we don't cool it properly, that's what happens. But even without that sort of evidence, the statistics all show that temperature is the biggest cause of failure for electronic equipment. And you can see the headlines all the time where people have significant problems. And these problems are going to get much worse. So, right now the computer manufacturers, and we work with them, have the problems. Electrical vehicles are an order of magnitude bigger problem. So, for example, the entire base of an electric vehicle is just one giant cooling system. Things like the charging thing. So, if you want to cool an electrical vehicle faster, you already have elaborate cooling systems in there. You want to cool them much better if we are going to be having fast chargers over there. What limits how fast you can charge a vehicle today is the cooling system. So, the simplest way of cooling any sort of a semiconductor assembly is a cold plate. And this is a very simple device. You've got an aluminum plate over here. You press fit a copper pipe into that. And at the interface, they put a thermal epoxy. And these are, they're called high thermal conductivity. Epoxies is not really high thermal conductivity. That's a pretty significant thermal resistance. And I'll talk more about that. So you design your semiconductor assemblies to fit on top. Now, one of the big problems with that is that when you do that, every component over there is emitting heat. And so your heat is not uniformly distributed. And depending on where it is located in your cooling pipes, you can have very different heat fluxes. Okay. And even though, in theory, every single component is below its limit, they're all at different temperatures and they're aging at different rates. And this is a serious concern because your circuit starts behaving differently as the components age. And so you might end up with a failure, even though in theory, every component is working fine, your circuit will stop functioning. So what you try and do is cool individual components. So this is for the Intel, what they're using for cooling their CPUs. And it's essentially, you have a microchannel heat sink over here, and then you've got a sort of cover on top. So you can pass your coolant through this out, and this is mounted right on top of the GPU, of the CPU. Now, the gaps between these are sort of about a millimeter size or so. So this is what you would call a mini channel. And if you aren't familiar with mini channels and micro channels, this is the classification which is in use. Ramesh Shah proposed this while back, and it's used pretty widely. Now, the reason that people go with micro channels, again, if you aren't familiar with this, if you remember your undergraduate heat transfer and fluid mechanics, after your entry length, you get a fully developed velocity profile and temperature profile, which means that the gradient over here is constant, and so your Nusselt number is now constant, right, for a tube or about order magnitude 4. But if that is constant, that means your heat transfer coefficient is inversely proportional to your hydraulic conductivity. The smaller you make your channel, the higher your heat transfer is going to be. And this is a very important fact, because then if you start looking at your heat transfer coefficient, every time you drop an order of magnitude, your heat transfer coefficient goes up an order. So in theory, what you want to do is instead of having one big channel, you want to have lots and lots of small channels. Of course, the limitation is that your pressure gradient is also going up, so your pumping power is going up. And remember, all of that power is being dissipated as heat inside your heat sink. So you could end up with a situation where you're generating more heat than you're removing, and you want to make sure that, typically you want to keep that about 2 or 3% of your total heat removal. So that is a very important parameter, and that limits how small you can make your channels. Okay, so now coming back from a manufacturing, it's nice to talk about having mini channels or micro channels. How do you make these things? Because there are lots and lots of them. So you can go by all the micro milling, micro EDM, which is how it's done, and all reasonably expensive processes. Everybody talks about 3D printing now, and certainly you can do that. And I'll talk more about that. What we want to do is we want to propose a new spray fabrication method, and that's going to be the subject, which we claim is very cheap and is very fast, and you can do all sorts of channels with it. Okay, so this is what is known as a wire arc spray. And this is a very well-known industrial process. This is not something that we are developing. It's used in industry all the time. And it's a very simple technology. You actually have two wires being fed in, you're striking an electrical arc between them, and you're blowing compressed air. So you can generate a spray, and you can do this with any metal. If you can buy metal in wire form, you can generate a spray. The spray then goes out, and the droplets freeze on the surface, and they form a really dense coating. Now, the equipment is very simple. So if you are familiar with a wire, welding, an arc welding machine, it's basically the same equipment over here. And so you can buy something like this for about $25,000, $30,000, and you are in business. Okay, so this is what our wire arc system looks like. You mount it on the robot, and you are spraying the metal. So these are now, you are generating a spray of molten metal droplets, and we can measure all the sizes and so on. Let me just say something about 3D printing. So I'm sure all of you have seen pictures like this, where people are doing really complex shapes using 3D printing. And these are great, except that each one of these is really expensive. And so, if you are making a rocket nozzle and $1 million is no object, great, do this. But things like heat sinks are commodity, products. Nobody is going to spend a couple of $1,000 on a heat sink. The problem is even worse because you want to make this with copper or aluminum, some high thermal conductivity. And if this is some sort of a laser process, you need very high power lasers to sinter, because all your energy is being conducted away by copper or aluminum. So aluminum and copper are the worst metals to work with. And that's why you'll see a lot of the publications, they'll use steel, and they'll make heat sinks out of steel or something like that. And the reason for that is that they probably didn't have a machine which could do copper. So just to compare this, your equipment is much more expensive. The biggest expense, one way, is the powders. So if any of you work with powders, powders are expensive things. Whereas wires are basically the cost of the bulk metal. That you're not paying much more than that cost. The other cost is energy. And if you are in a place where energy is expensive, so I just spent a couple of months, I was doing this talk in Japan. I was telling those guys that for what you're paying for energy, actually there are a lot of Germans over here, what you guys pay for energy as well. At least in Canada, energy is cheap, so I don't worry about it that much. But in any case, the energy costs are huge for this. The time, also the size, all of that are concerned. So there are real limitations to what you can do with 3D printing. Okay, so what we want to do is we want to use this additive manufacturing method, and we want to make heat sinks which we think will reduce the weight and size, increase the heat transfer. We want to minimize the temperature gradients. And this is a sort of, you don't think of this consideration, but one of the biggest reasons why they don't want to use liquid cooling in these is this problem of sealing. Because your seals fail, and there's nothing which gives a computer engineer more nightmares than water in their computers. And so we want to get rid of that as well. And then we want to enhance two-phase flow. Okay, so let's start off. So this is an off-the-shelf heat sink, which you can buy. I think it costs about $100 in Toronto. And it's very simple. So we started thinking, how can we improve on this? So the first idea was that we would take aluminum plate the same size. You just machine a groove in that, and then you 3D print a tube. And this is made out of PVA, polyvinyl alcohol, which is a water-soluble polymer. And you can 3D print very nicely with this. We fit it inside, and then we take it and we spray metal over that entire surface, and we fill in that gap. So when you take it out, this is what it looks like. We machine the top, we put this in water, and we dissolve out that pipe. So now you just have a hot inside. And we've got a heat sink. But now, of course, we are no longer limited by this radius. The original radius was because the bending radius of that tube. So we can do something like this, and we can put 4 passes inside that. And when you test it, so this is the thermal resistance of a commercial one, this is the 2 pass, this is the 4 pass, and we've improved it. So this is nice. But now you can really make complicated ones. So this is a miniature heat exchanger. So this thing is about 1 millimeter wide. The whole thing is about 56 millimeters square. We spray it on one side, we do the same thing on the other side, and you've got a tiny heat exchanger, very efficient. We've tested these, and so you can make very effective. So we can do very complex internal channels using this sort of a technique. Now, this was an actual project. We were working with our electrical vehicle group over in electrical engineering, and they were making a DC to AC converter. And this is what their board looked like, and this is the heat sink that they were using. Now, in this, most of your heat, there's a row of components here, another row over here, and all your heat is being generated out of that. You also have 2 big inductors, and those are generators. And we're saying that, can we put our channels right underneath these and machine a really small piece, which would put the cooling channels right underneath. So we start off with aluminum plate. Here again, 3D printing out these PVA inserts that we put inside there. And now you don't actually need to be circular. We could make sort of very thin. So these are about, 1 millimeter. These are about 3 millimeter high, 8 millimeters wide. We spray metal on that, we cut it to size, and this sits right underneath the circuit board. And your heat emitting elements are right over here, the inductors are right at the end. And the thermal performance is slightly better, but that's not really the point. We've reduced both the volume and the mass by about 90%. And on an electrical vehicle, this does matter. You want to reduce the mass of the vehicle. So we can custom make these heat sinks. Okay, so this is sort of one technique. But then we said, can we use our spray to make surface features? So now, instead of using our 3D printing as sacrificial, we can make a mask. We can 3D print a polymer mask, right? So we 3D print a polymer mask, and we had openings in all sorts of different shapes. And we wanted to see what sort of a resolution we have. So if you look at these ones, so there's this little airfoil shape, and something down to about 1 millimeter, you can retain that shape quite nicely. One other thing I'll point out, you see around it, these are satellite particles. So if you have an opening in a mask, small satellite particles get through. So all around your structure for about a distance of about 1 millimeter, you've got these little particles which have landed. And I'll come back and talk about this because I want to show that this is not actually a bug, it's a feature. Okay, so just to show, for example, with aluminum, this is the mask. We can think of that, the mask being over there. After 8 passes of our spray gun, and you sort of grow these, and now these are satellite particles in the region between them. And we can do this with copper as well, and you see this sort of a columnar structure growing. So people have been trying to make structures. We actually just grow these structures as part of the process. So now the idea is that if we are given some sort of electrical architecture, so the distribution of heat sources, you can do a simulation. There are lots of software packages that will do a nice simulation, which will tell you where your heat dissipation is taking place, and you can get a heat flux or thermal contours of that. Now we want to use a topology optimization method and design a circuit board, a heat sink, which will direct the liquid where you want it. So you don't need channels or anything at all. If you do that, what your topology optimization gives you a shape like this. So if you can think of the liquid is coming in from the top, the red are the solid, the blue is the fluid, and the location of the solids is directing the flow to where you want. And now by using our method, we can actually make these very quickly. It takes us about 20 minutes to spray that. Okay, so let me just say something about topology optimization. I'm not an expert on it myself. This was actually a collaboration with one of my colleagues who is an expert on this. But the idea basically is that you've got a heat source. This is your design domain, and we are doing only half of it for this semester. So in this design layer, you have to define what your objective function is. And we had over here 2 objective functions, or 2 performance metrics. One is the thermal resistance. So this is the heat sink temperature minus the water inlet temperature. Normalize it by the power of the source. Right? And we want to minimize that resistance. But the other thing is we want to look at the difference between the maximum and the minimum temperature in the heat sink, and we want to minimize that. So we are trying to minimize both the resistance and also at the same time the temperature gradients across them. So our objective function, we just decided to take the sum of those two. And you could, whatever objective function you wanted to weight them or something, it's really up to you. And what we are doing then is we are solving, this is essentially your entire fluid thing. In this, we are filling this with a porous medium. And the porosity is variable, so you can make it either 0 or you can make it 1, where it's either solid or it's liquid. And your optimization routine is running through that, changing the porosity at different rates until you finally come to a solution. And then wherever your porosity is 1, that's where the fluid is. Where your porosity is 0, that's where your solid is. And so that is how you come up with this. Okay, showing the fabrication. So we take a metal plate, we put about a 3 millimeter deep cavity inside that. We 3D print out of polymer now a mask. We fit this inside. We spray the metal on that. And then you remove the mask, and this is what you are left with. These are the structures. And then we take it and we grind it down. So you've got a uniform height, in this case is 0.75 millimeters. Now we want to seal it. And so what we do is we do a lid over here, and we leave a little gap between the lid and the surrounding. And then we spray metal inside that, and that seals it. So you got like a 2 millimeter thick layer of metal inside that, and that seals the whole thing in place. You grind it down, and you essentially have just an aluminum plate with a lid. Okay, we build our flow loop in that, and we set this up. So essentially, we've got a heater block below. This is a heat sink over here mounted, and that the top is just for the headers for the inlet, outlet, pressure transducers, temperature, all of that. So let me just say, so we compared it to a standard straight heat sink, a parallel channel, and we actually sprayed that one as well. So, we can spray anything that you like. So we actually made this by spray. This is optimized. So the water is coming in at 21. And if you see, the temperature on the heat sink varies from 43 all the way to 55. With that one, we are going from 42 just to 48. So we've actually reduced the temperature difference significantly. Okay, so we can compare the thermal resistance for the parallel and the optimized, and they're a little better, not a whole lot better. But this is what we are really looking for. This is what we define the temperature non-uniformity. So it's the maximum minus the minimum, and we've normalized it by the heat sink temperature minus the water temperature. And this is much lower for optimized, and it stays constant independent of the flow rate. And the price we pay for that is slightly greater pumping power, but this is so much smaller than the power that we're moving that we don't really worry about it. Okay, so now we can actually optimize it for, this is a uniform heat load, but if we had a localized heat load, we've run the optimization and we can spray one for that. This is if we had just a single heat load, and our optimization is saying that, well, block off most of it and just let the water run underneath that. And so, given any sort of a heat distribution, we can spray a corresponding heat sink. Okay, now let's come to the second part where we are going to talk about the flow boiling, right? And so everybody is again shown this sort of thing with the flow boiling. So far we've looked at single phase where we are increasing linearly with the heat, that's the water temperature. But if we get into nuclear boiling, we would expect an order of magnitude increase in the heat phase. And so what we would really like to do is work in this region where you have nuclear boiling and you start seeing this sort of nuclear bubble nucleation inside. The thing is, nobody does this, right? So commercially, nobody's got over there. And the reason simply is because of the instabilities. So what happens is that if you start getting boiling inside your microchannel, you get a bubble, and the bubble grows very rapidly, and it fills the entire microchannel. Now it doesn't have any place to grow, so it starts growing in both directions along the length, and it actually starts pushing the liquid back. And so this essentially blocks all your flow through your heat sink. And it can cause all sorts of trouble, but this is so unpredictable and so hard to control that until now, nobody's sort of seriously using two-phase flow in things. Right? So in this, what we wanted to do was, we actually decided to try this out from there. So we machined this. Again, we 3D printed our polymer mask, we sprayed, and this is what our parallel heat sink looks. So we've sprayed this. We sprayed this out of aluminum. We sprayed one out of copper. And this, if you see the section out of the aluminum and copper, and you actually focus in over here, this is actually a great boiling surface. People spend a lot of time trying to make porous surfaces. They use femtosecond lasers to put them and make new nucleation sites. We just, by the process, we get a great set of nucleation sites. This can also I'll show you, it can be very hydrophilic as well, especially the aluminum one, if you can treat that. So we put it in the surface profiler. So we machine one like this out of aluminum. And you can see the black one is the profile of the machine one. The sprayed ones, you don't get such a neat one, but it's about the same flow area. So we have a flow area of, this is 2 millimeters wide, 1 millimeter high. So it's about a 2 millimeter area. In machine one, the second one, we machined it and we grit blasted. So the surface roughness for this was about 0.2, this one about 3 microns. Our wire arc, you'll see, and the sprayed ones are both, the roughness is much higher. We have a roughness of about 12 microns over there. Okay, so if you look at the surface wettability, this is the aluminum one. And this, if you look at it from the top, this is sort of what the structure looks like. And you put a water droplet on that, and it just soaks right in. So this is a very hydrophilic surface. The copper is not so much. So this is what the copper looks like, and you put a droplet on it, and it can take quite a while to soak in. And this is because of the oxidation of the copper, which makes it more hydrophobic. Okay, so we wanted to go out and test this. We built a flow loop. This is a test section. We put a chiller, and we are running water through it. So this is what the test section looks like. We've again got a heater block. Over here, this is the sample plate. We put the sample plate over here, and then we've got a transparent polycarbonate plate on top, in which we can put all our headers, and we can also put our high-speed camera to look at. So we are measuring the heat flux. So the heat flux is the electrical energy supplied. We are losing about 10%, so we subtract that, divide that by the area of the heater block. That's our heat flux. This is the mass flux. So we are taking the total mass flux of water going through, dividing by the cross-sectional area. And I'll show you results at 300 and 400 kg per meter square. Second, which is, you'll find a lot of in the literature, people tested it at about that sort of mass flux. Okay, so this is the first one. This is the machine. And this is what it looks like. So this is the single phase. This is the two-phase region. And this is actually, this is the video. And if you sort of look very carefully, you might see a couple of bubbles moving. It's hard to see from that. Okay, so this now is the grit blasted one. And in this case, the bubbles are more visible. You can see them. And you can see how increasing the roughness increases the heat transfer quite significantly. And so you get much more nuclear boiling. This one is the aluminum wire arc. And so we've increased that even more. And this finally is the copper wire arc. So they're all sort of lying around over that. So our surfaces offer much higher heat. This is at 300 meters per second square. And again, you can see our wire arc. This is the wire arc copper. Now, the limit on what we can do with this is because of the instability. So let me show this. So you can see the flow. Watch this one. So this bubble will suddenly grow and you get dry out. This is the incipient instability. So you got bubble growing, it fills the whole thing, this starts happening to other channels, soon you have no flow inside your heatsink at all. Now, people are trying all sorts of different things. I just met a couple of students from Guwahati who are trying exactly this thing. So what do you do to try and prevent this? One idea is you have a diverging channel, so you get less, and you're essentially trying to push it. The other is to, instead of having channels, you've got some sort of a porous media over there. We came up, so this is the idea of the ratcheted surface. And I'm sure a lot of you have seen this. There are a bunch of videos around on that. So this was one particular paper years ago, self-propelled Leidenfrost droplets. The idea is if you put a Leidenfrost droplet and the surface and you have this sort of a sawtooth structure, the forces acting at the bottom are asymmetric. So it will tend to drive it in one direction. And they had a very cute little video up on YouTube, so I thought I'd show that to people. So this is, they make a ratcheted surface, they put it over there, then you put it on a heater and heat this up, I think, to about 220 degrees C, and then you put a water droplet on that, and it'll keep running. It's self-propelled. So you can do this with a droplet. You can do this with a bubble. So this is another paper, the group out at Auburn University, and they're looking at bubbles in channels, and they've got this sawtooth structure, and they can drive the bubbles in one direction as well. So we said, okay, this looks like a nice idea. Okay. In this, by the way, for the boiling, they actually had to machine cavities inside each one of that to act as a nucleation site. So if you just try and machine it, it's actually a very poor boiling surface. So what we did is we made a mask, but we've got the openings are inclined at 30 degrees. And so all of those openings are at 30 degrees. And then we set this up and we incline the surface at 30 degrees. So we are spraying along the openings. And what you end up is structure like this. And if you take a cross section of that, you've got this sort of sawtooth structure. The surfaces, it's a nice boiling surface. You have reciprocity on that. And you expect that to drive. Okay, so we tested it. So we heated it to 110. We are not getting into Leidenfrost. This is strictly nuclear boiling right now. And so if you put a drop on the side, nothing much happens. It just kind of, but if you put it on that, you're actually driving them quite nicely in one direction. So you can actually get a movement of the liquid even if you get boiling if you do this. So we decided, can we make sawtooth channels? So in this idea, we 3D printed out where there's a sawtooth structure on the walls, right? And you spray this, and what you end up are the channels, except now they have this little sawtooth structure. And so now we go back and we test this. And so now we are right at that limit, you know, where we are getting dry out. But now look what's happening over here. The liquid is actually trying to push that down. So you try and get dry out. It actually looks like it's being pushed down. And that was at 330, we increased this up a little more. And now you can see it's becoming harder and harder to push it down. Okay, and you can see the instability, but it's still, and we are right at the limit of before we get the instability. But you can see if we put the wire up. So with the wire arc with the sawtooth, we are actually getting higher heat flux, and we are hoping to be able to push out where the instability happens. So this is sort of very new work. It's still ongoing work a student gave me that only a couple of weeks ago. And the idea is that now that we can make any sort of a structure that we want, what sort of structure could be used to actually delay impulsive boiling and stabilize our flow? That is the problem, and we've got lots of different ideas which we hope to do in the next one. Okay, so let me try and conclude. So we actually use this to make heat sinks. We've got different ways of doing it, but we can actually make very complex geometries, and we can also improve flow boiling. And this is a technique which actually, if you wanted to use this, it's quite easy to scale up. It's a very robust sort of technique. And the Y-arc spray is very well understood industrially, so it's not something. So I will stop over there, and I will be happy to.
Yeah.
What is thermal conductivity of this sprayed block technique?
Yeah, so the thermal conductivity of these are less than the bulk material, and it can be low as about half of the bulk material, because they are slats which are sort of bonded together, and you actually get oxide at that interface. It's actually not that serious a concern in this application, because if you look at the thermal resistances, your convective resistance is about an order of magnitude higher than your conductive resistance. So even if your conductive resistance increases by a factor of 2 or something like that, overall it's still negligible. It's all about the convective resistance.
I agree with your point that additive manufacturing is very expensive, especially if you're trying to go much smaller length scales.
Yeah, and it's very hard to scale up. So I don't see it ever, any sort of a mass production. I just don't see it happening. You have very specialized applications where it might be, but something like a heat sink is not an expensive product.
Could you also go for stainless steel with this production method?
Oh, you can do anything. If you can give me a metal which I can get in a wire,
Okay.
I can spray. So we've done stainless steel, we've done nichrome, we sprayed all sorts of things with nichrome, nickel, basically all sorts of alloys, aluminum alloys. So we can get wires and just about anything.
Okay.
Very, very interesting technique. The typical size of your channels is millimeter.
Yeah.
So of course you get this porosity, which has an excellent feature. Yeah. But could you simply just drill, if you calculate how the flow should be distributed, you could also drill it. Then you don't have the porosity, of course, but it's maybe a cheaper process because
No, so if you go and talk to your machine shop and ask them to sort of mill out one of these things, they will ask for a month and they'll charge you a lot of money. We've tried that. Even machining straight channels is an expensive process. Using just milling it or they use EDM or something like that.
it's a millimeter size. It's typically easy to do.
It is, but we can do it in 20 minutes. We spray it,
That's right.
and it can be as complex as you want. So especially when
But you need to produce your mask before.
the mask printing out in polymers is that we do all the time. That's really not.
Nowadays we
And
have
we can reuse.
tabletop 3D polymer printers, tabletop ones that we can get.
Yeah. So
can do it.
this is just in fact the one we have is actually an open source one, because the commercial ones aren't set up. You can't use PVA. You can't use the water soluble. They're not really designed to do that. They use the water soluble as their sacrificial material when you're trying to make voids inside. So we've got an open source one which we can mess around with, and we can put anything. We put the PVA and print it out with that as well.
Maybe comment to that. I think putting material to a substrate has the great advantage that you can do something in between. So when you mill it, for example, you can just take it away and it's always straight. But if you, let's say, formulate the question, if you have two masks on top of each other, so spraying it first and then putting another mask and
Yeah.
spraying again, then you might also get a reentrant structure.
Yeah, so we've done, so we can also use materials, right? And I didn't talk about that, but if you wanted to put a coating inside your, inside the heat sink, we can do
So-
things like that as well.
Can you, for example, spray stainless steel on copper?
Oh, yeah, absolutely. So, if you wanted some sort of a non-corrosive coating or something like that,
Yeah.
we can do ceramics on, if you wanted something really, we could do a protective ceramic coating inside.
Sir, when you do this optimization, how I forgot the slide number actually, but how this pressure drop, the pumping power increase, like what was the before optimization and after optimization?
So, I mean, if you wanted to do optimize for the pumping power, you can do that as well.
Not optimization of the pumping power, sir. I'm asking like optimization of this cooling.
Heat sink design, you mean
The
the
heat sink
topology of the heat sink?
Yes, topology
Yeah,
optimization.
pumping power difference was actually very small. It was only a couple of percent change. So that wasn't something that we actually worried about.
So absolute value is small, but percentage wise it might be.
Yeah, I can show that.
Yes. Next, I guess.
So your question is in the optimization, he can make use of the pressure drop also as one of the criteria or objective functions to optimize?
So this is the difference between the parallel one and below and the optimized. So you do increase, but this we are calculating in terms of the pumping power, and we are removing about 500 watts. So 0.1, 0.2 watts is really not that big a concern over here. But you could certainly use, if that was a concern, you could optimize for minimizing the
Pumping
pressure drop.
power. Because anyway, you do the simulation for the heat dissipation and then you
Yeah, you
so you
I
can
mean,
also do
you
the
solve
flow,
the entire fluid
flow
mechanics and
simulation
heat
and then
transfer.
you can.
So you could pick anything you want as your objective function.
Very nice application of this spray coating technique. So if I understand correctly, so you have this setup, which is coming from the side and it is vertically up, and you have this sawtooth side one. But if you make this thing horizontal, then you need to completely change the design like that. My understanding is correct.
You talking about the design of the heat sink itself?
Design of the plate, design of this channel. So
I mean, gravity is not really a concern in this. I mean, it's just
the flow loop, because flow is happening, right?
because flow is happening. So for single phase flow, the whole thing is filled with liquid. For two phase flow, it might become a concern. We haven't really got to that point as if we're just doing it horizontally. But for single phase flow, the whole system is liquid filled.
Yeah, that I understood. But so if you so you show the results in a millimeter scale channel, right? That after some time when you increase the heat flux or increase the temperature, you need to have this kind of techniques, surface texturing, to remove the bubbles out of it. But if you go for a centimeter scale, so do you still think that this kind of techniques is needed to remove the bubbles, or do you think that flow itself can, convection can itself remove this bubbles from the surface?
Yeah, so I think the whole idea is that you want to use small channels. If you have like a big plate with a 1/4 inch, and that you would need a huge amount of heat flux to actually get boiling in that sort of a configuration, where you have 6 millimeter tubes. You probably could get away without this, but your thermal resistances would actually between your heat source, and that would be so large that it wouldn't really help to have boiling.
Sir, how do you find out or locate those hotspots? It is by numerical simulation or you?
So it's numerical simulation, but you also usually know. I mean, these are really small components. Sitting on a board. I had other things, examples, where we show that, but these are transistors which are a couple of millimeters. They're sense. So they're pretty, small heat sources on a fairly large board. But the simulations actually are pretty effective. They'll tell you what the distribution, what your heat flux distribution is. Quite well. Yes.
So one thing that probably I didn't understand is the effect of the velocity of the compressed gas that's coming in the arc deposition process. So is that going to influence obviously the roughness of the spray, and that's going to again play a role in the enhancement of nucleation and slow boiling?
I mean that is a whole different subject, which we also do. But optimizing the spray process is a whole process. So when we got to this, I mean, there's so many parameters.
So how do you set these parameters? I mean, when you...
So it's a lot of trial and error.
Okay.
I mean, we spent years trying to make more of a science of it, but in the end, a lot of this is trial and error. So, there are things like the standoff distance, the arc voltage that you use, the power which is given. There's all sorts of parameters. And it's still quite an art, rather than a science.
But the overspray, so to say, it doesn't matter. It doesn't cost you anything. So the stuff that doesn't go through the mask.
Yeah, in this case, it's usually not that big a concern because these metals are relatively cheap. So it's not that big of a concern.
And the process works like that you, let's say by the arc, you produce a liquid droplet, and this is blown by air liquidly on the surface and solidifies. Yeah.
So people are doing, not with this system, but with what is known as a plasma, where you have a plasma jet coming out. And what they are introducing are either suspensions or liquid suspensions or liquid solutions. And you can do all sorts of very interesting things with that. That is a whole field in itself. And those are actually most useful when you're doing things like ceramic coatings, because you can make a ceramic suspension of the ceramic, introduce the droplet spray into that flame, and the liquid evaporates, and the ceramic particles then land on the surface. For metals, not so much. It's not really worth it.
Is it available in here in India? This
you have a bunch of manufacturers over here for this. This is a very common technology.
Just a commercial device.
Oh yeah. Make a couple of phone calls. I'm sure in Chennai there are a bunch of suppliers.
Okay. Amazon India.
But this is very well known technology. On your anti-corrosion coating, so you've ever seen the anti-corrosion coatings, on bridges and ships and things like that. They all spray zinc using this kind of a technique. So it's very standard.
Would there be any introduced porosity at the junction where the coating is attaching to the base material?
So in the coating itself, you get about 2% porosity. We've actually done a lot of work to increase that porosity. With Marco, we did a whole thing where we made heat pipe wicks, and we got a porosity of up to 44%. And we did that, you can do it by putting two metals inside there and then dissolving out one. And we can get 40%, and we can make very nice wicks for heat pipes using this technique. And the advantage is that it's really bonded to the substrate really well. You don't have to worry about that. And we can coat as big a plate as you want.
So what liquid pressures have you been tested for?
Sorry?
To what liquid pressures have you been tested? Like at higher liquid pressures are there any leakages?
We didn't really go to high pressure. I mean, there's no real incentive right now to go to very high pressure. I think we tested that to, it must have been 60 psi, which is about 400 kilopascals or something like that. We tested to that. But that is sort of ongoing work. We are working now with somebody wants to use for battery cooling and so on, and we are actually doing tests where we are going to pretty high pressures. And we also are doing a whole series. I have a student actually who's doing precisely that right now. Up to about 4 atmospheres or so, you can go without any problem.
So I have one query. When you are making this mask, etc., like using this 3D printing, does it require any specific type of, because the distances here are very small, so is it like is that part expensive or that?
No, so you get high temperature resins for the 3D printers.
I'm talking about the accuracy of that.
Oh, the accuracy. So yeah, the accuracy, it's probably less than 0.5 millimeter or something like that. And if your shape is less, the ones which I showed over there, where you can actually make them. Here, so this is the one which I showed over there. And we were trying to see how, fine can you go and still sort of retain the shape. So if you see, down to about 1 millimeter, after 1 millimeter, it really becomes difficult. I don't know how you quantify all of that, but less than 1 millimeter, you don't really retain the shape over there because it's a masking process. But anything above that, things like channels, or if you have a couple of millimeters size, you can actually get the shape quite accurately. Fortunately for this sort of application, it's not a high precision. You just want the liquid generally, where
Maybe tomorrow.
How does the lid bond to these projections?
it doesn't. But our heat conduction is from below, so it actually doesn't matter. So the lid is just sitting on top, so it's actually pretty poor heat transfer from there. If you really wanted, we actually did one where we filled the whole thing with the PVA paste and sprayed metal on top and then dissolved that paste, but that's messy and complicated. So
it doesn't really matter even if the lid is not.
It doesn't matter because your heat transfer is from below.
Okay, so please, last question.
Professor, I saw that you have used graphene as TIM. Is it a cost-effective TIM, or could you suggest any other?
Oh, so this is a pretty effective TIM. So one of the biggest problems we find is that you can improve your heatsink design and reduce its resistance, but you hit a point where the resistance is less than that of your thermal interface. And that becomes a real problem because then improving it further is complex.
Yeah.
So we spend a lot of time trying to
TIM
find.
is always the bottleneck.
That is the bottleneck. If anyone has a good idea for a TIM, you will make a lot of money on that. but so we spend a lot of time trying to find good TIMs with a low resistance, so at least we could show the improvement in our heat sink.
Is it a cost-effective one, or graphene sounds expensive?
It's reasonably expensive, but I mean, it's not like we are buying them in bulk. We only want 1 or 2 pieces.
Okay, so let's thank the speaker again.
Thank you, Professor, for coming here. I request Professor Marco.
Thank you.